I hope the previous live session videos are available to you guys, right? So the links are shared, no? Are in the link
Yes.
shared? Yeah, today I hope the links are shared. Okay. So weekly, there are the following topics. So we have we discussed several properties of the signals like the even symmetry, odd symmetry, what are even signals, odd signals, and then we also saw what orthogonal signals are, right? And we have seen several examples with respect to even, odd, orthogonal signals. And these are all defined for real signals. And orthogonality is also defined for complex signals. But when we go for the complex signals, we have something known as conjugate symmetry and antisymmetry, which we have seen. And we also saw what we meant by the periodicity of signals, right? So we were at this during last week live session. I mean, not last week. I think in the last live session, which happened on Wednesday. So today I'll be talking on these three topics. Hopefully, the correct video is uploaded, right? This was the concern raised
Yes, ma'am.
Wednesday's class. Yeah, the correct video is uploaded. All right. So topics that we would discuss today are the continuation of week 3 and the topics are manipulation of periodic signals, okay, power and energy. Okay. So how would you guys like me to do it? Do you want summary on these three topics, or do you have any specific questions to ask?
Summary, ma'am.
Okay. So remember periodic signals. So when do we call a signal is periodic? So just the definition, recap of the definition. Uh, a signal x of t is said to be periodic if x of t is equal to x of t plus t for some t. Okay. If there exists some t such that x of t is equal to the original signal such that x of t plus t is equal to the original signal x of t, then such a signal is known as the periodic signal. So if this happens, then we call the signal to be periodic. And the period of such a signal, this is also known as fundamental period. Fundamental period of such a signal is minimum t such that x of t plus t is t. Okay? So I repeat, if at all for a signal x of t plus t equal to x of t for some capital T, then such a signal is said to be periodic. And the period of such signal is the minimum T such that this happens. X of T plus capital T is X of T. Okay, so that is known as the fundamental period. This is also denoted by T naught or T. If we are denoting this by T, then maybe we can denote it by T prime. Okay, right? And the fundamental frequency is 1 by T naught. Remember, frequency is always 1 by T. So the fundamental frequency, which we denote by F naught, is 1 by T naught. And the fundamental angular frequency, which we denote by omega naught, is 2 pi F naught. Okay. And yeah, so this is with respect to the periodic signals, and we say a signal is not periodic if x of t plus t not equal to x of t for all values of t. Or if I call this t prime, x of t plus t prime not equal to x of t for all. So there is no value t prime such that x of t plus t prime is equal to x of t. Then such a signal is called a not periodic signal or aperiodic signal. Okay. So periodicity has two types of signal. One is the periodic signal and the other is aperiodic signal. So x of t plus t prime is equal to x of t for some t prime. The complement of that is aperiodic. What is the complement? X of t plus t prime not equal to x of t for all values of t prime. Okay. And when we have the periodic signal, we have period associated to it, and the period t naught is minimum t prime such that x of t plus t prime is equal to x of t. And f naught is 1 by t naught, omega naught is 2 pi f naught. Okay. So that is all with respect to periodic signals. Let's see a couple of examples, which I think already professor discussed in the class. I would like to just pick up those examples and show you what this, um, how to calculate the period and all. We'll also look at the period of the sum of two signals, the product of two signals, that will go in like couple of minutes. But then, when before going there, let's see a couple of examples on the periodic signals. Okay, so let's take this example, which was already discussed in your class, which I would like to again recall. N from minus infinity to infinity. Okay, so is the given signal periodic? So how do we check if the signal is periodic? Let's try to plot and see how the signal looks like. So what is rect of t? The rectangular function is defined as a box, right? From minus half to half. We have t here. This is rect of t. Now given t equal to 2, for n equal to 1, okay, what is rect of t minus 2? Remember the shifting operation. So how do we do that? So this is rectangular function of t minus 2, t correct? So
Yes,
this
ma'am.
is rectangular t minus 2, right? No? So let me also see for n minus 1. When n is minus 1, what do we have? That is, so I'm trying to evaluate each of these terms for every n, and then I'll sum it up. Okay? So we have a sum over n from minus infinity to infinity, rectangular of t minus nt. So I'm plotting each of these terms for every n, and then I'll try to sum it up. Okay? So my individual rectangular functions look something like this. So for n equal to minus 1, this is rectangular of t plus 2, right? And how does that look?
Shifting left by 2.
Is this correct? Yeah,
Yes, ma'am.
this is rectangular function of t plus 2, right? And then for n equal to 2, what do we have? Rectangular function of t minus 4, right? And how does that look? How does that look? Correct? Yeah.
Yes, ma'am.
And similarly, we have for n to minus we have rectangular of t minus 4, which minus 3 point minus 4 minus 3.4 and 9. This is rectangular of t plus 4 or t. Similarly, we have like of such blocks n into infinity, and on
Excuse
the
me.
negative axis also have into minus infinity, right? Yeah, you're
Your voice is
asking.
breaking, ma'am.
My voice is breaking. It's not audible. Let me check. Hello.
Yes, ma'am. Now it is okay.
Any better? It's better, right? Or is it still breaking?
Yes, ma'am. Now it is also breaking.
Now, what should I do? Do you hear disturbance or is it breaking?
What, ma'am? I
Do you hear disturbance or the voice is breaking?
voice is breaking.
Ah, Hello, Ramit, are you there?
Yes, ma'am.
Hello.
Hello. Yes, ma'am.
Yeah, can you hear me now?
Yes, ma'am. Now it is clear.
Yeah, there's some internet fluctuation in the place uh, that I'm staying in. So let me know if something breaks down, okay?
Yes, ma'am.
What happened to Satyam? Did he leave?
Yes, ma'am.
Okay, he rejoined. Okay, great. Right. So we have, yeah, for uh, as n goes to infinity, we have, many such blocks. And as n goes to minus infinity also, we have many such blocks. And over, we are summing this over all n, right? Oh, my screen is visible or is my screen visible?
Not visible.
Oh my God, there is serious internet problem in the place I'm staying. Okay, thank you. Let me try to rejoin. Hmm. I'm sorry guys, just give me like a minute. There are a lot of technical problem here. All of a sudden, for some reason, the internet in my iPad is not working. That's the issue I'm facing. Only it works in like. Okay, it's not allowing me to join. All right, let's figure out something. Do you have any specific questions, or can we do the recap on these three topics maybe on Wednesday's live session? If you have any specific questions regarding your assignments, I'm available for another half an hour to explain them to you using some other whiteboard or something. But to give the summary, oh, it allowed me to join. Wow, great. I'm audible, right?
Yes, ma'am.
Okay, great. So my screen is visible now, right?
Yes, ma'am.
Oh, good. Right. So what I'm trying to say is, so we are trying to see if the given signal over here is a periodic signal or not periodic. What we have done, before Subhash joined is we were trying to see how these rectangular functions look like for each n, and this is how they look like. So for n equal to 1, this is what the rectangular function is, and for n equal to minus 1, this is what it is. Likewise, for n equal to 2, n equal to minus 2, and as n goes to infinity, we have such rectangular blocks which do not intersect, and also for n equal to, as n goes to minus infinity, we have other rectangular blocks on the left hand side which do not intersect, and when we add them up, sum over uh, n from minus infinity to infinity, rectangular function of t minus nt when t equal to 2. This is something which looks like this. So we have the first rectangular block that is going from minus half to half, and the next rectangular block which goes from what? Which goes from 1.5 to 2.5, and we have another rectangular block which goes from uh, 3.5 to 4.5, and we have many such rectangular blocks on the positive side, and also on the negative side we have minus 3.5, minus 2.5, minus 1.5, minus 4.5, minus 3.5, and so on. So this is what our summation. So if I call this as some y of t, this is the function y of t when we plot on the time axis. This is how this looks like. So now let's see if this is periodic or not periodic. So this is our y of t. So let's try to calculate y of t minus 2. Okay. So what is y of t minus 2? If you plot y of t minus 2, what happens? The block that I am filling now. Okay. So this gets shifted to and the block that I am filling in blue gets shifted to 3.5 to 4.5. So this is the block in blue. And the block I fill in green, that gets shifted to, and so on, right? So this is y of t, and this is y of t minus 2, right? So if you could see, your y of t signal, as long as this is 1, your y of t is exactly equal to the signal y of t minus 2, right? So there is no change in the signal even after you shift it with respect to the time axis. Similarly, if you evaluate, your y of t would also be equal to y of t plus 2, y of t would also be equal to y of t minus 4, and y of t plus 4. So all these signals are equal for this given signal. Okay. So since there exists some t, so what are all possible such t's? 2 or minus 2, or you know, 4 or minus 4, all these are possible values, right? So there exists some t for which y of t equal to y of t plus t. Okay. And what is the period? I think I made a small mistake in the definition of the period. Period should be mod of minimum. Okay. Okay. So what is the period here? So period is what are all such possible t's for which possible t's are minus 2, 2, minus 4, 4, minus 6, 6, and so on. So for all these possible t's, we have y of t equal to y of t plus t. And period is minimum of mod minimum of all these values. And what is that? Which is simply 2. The period of this particular signal is nothing but 2. Okay. So likewise, similarly, you can evaluate for any given system. And also, like we told, so this particular signal is running on infinite time axis. So it takes values. So the signal is defined from minus infinity to infinity. So for all values from minus infinity to infinity, the signal is defined. Such signals are called infinite time signals. And one thing that we learned from our last class is all finite time signals are aperiodic. Okay. Finite time signals are aperiodic. And for infinite time signals, we have to check if the signal is periodic or aperiodic. Okay. And another example I would like to give is uh, sine omega naught t. So if you plot this sine omega naught t, what happens to this? At t equal to 0, the sine value is what? 0. And at t equal to, so this is 2 pi f naught t, right? So at uh, t equal to 1 by 2 f naught, right? At t equal to 1 by 2 f naught, we have sine pi, which is again 0, right? And at t, sorry, t equal to 1 by 4 f naught, we have this as 1, right? Right? So this is our sine signal. So this is 1 by 6. Uh, so this is, so 1 by 4 f naught. when t is 1 by 4 f naught, our omega naught t is 2 pi f naught t, which is 2 pi f naught times 1 by 4 f naught, that is pi by 2. At pi by 2, sine function takes a value 1, right? And when t is 1 by 2 f naught, 2 pi f naught t is just pi, and sine takes a value 0, right? And then I want 2 pi f naught t to be equal to 3 pi by 2. Then what is t? 3 pi by 2 times 2 pi f naught. So that is 3 by 4f. So this is 3 by 4 f naught, and this is 1 by f naught. Okay. So this is how the sine signal is defined for these values. And as you go forward, it just keeps repeating the same. Maybe I should plot with a different color. Right? So as you keep going forward, the same signal keeps repeating, right? So if you see same signal keeps repeating, implies the signal is periodic. Okay. So the same signal, whatever you plotted within this range, if you see the same signal keeps repeating, right? The same signal keeps repeating even on the left of that signal and even on the right of that signal. If such a thing happens, then that signal is periodic signal. And how to calculate the period? So what parts of the signal are repeating? So from here until here, that is the part of the signal that keeps repeating. The period of the signal is the time frame exactly where the signal gets repeating. So this part of the signal is repeating, and the period of this signal is 1 by f naught minus 0. So 1 by f naught, which is t naught. The period of this signal is t naught. And what is t naught? It depends on omega naught. So here I am taking omega naught to be a constant. Suppose if you are given sine 6 pi t, okay, the period of this signal is what? So this is 2 pi 3t. So my f naught is 3. So my period t naught is 1 by 3 for the sine signal. So this is for the sine signal. So I calculated the period for any general omega naught. So for any general omega naught, the period of the signal is 1 by f naught. And how do we get f naught? F naught is omega naught is 2 pi f naught. So if you are given, suppose if you are asked to find the period of the signal sine 7 pi t, so this is our omega naught. So omega naught is 2 pi f naught, which is equal to 7 pi. So your f naught is 7 pi by 2 pi, which is 7 by 2. Hence your t naught for this sine signal is 2 by 7. Is that okay? Similarly, if you evaluate the period for cosine signals, so if you have a cosine function cos omega naught t, the period of cosine function will also be 1 by f naught. The signal keeps repeating in between the frames 1 by 0 and 1 by f naught. So the period of that signal is whatever the signal that you see in between 0 and 1 by f naught, it just keeps repeating even towards your right side and even towards your left side. Hence, the period of the cosine function is also 1 by f naught. Okay, is this clear? So the period is defined for all infinite valued signals. So for all finite time signals, all those signals are aperiodic. Suppose if the given signal is infinite time signal, then we have this property of periodicity or aperiodic. Suppose if the signal is periodic, we also have the fundamental period to it. Fundamental period is the basic part of the signal that keeps fluctuating from minus infinity to infinity. the same part of the signal keeps repeating from minus infinity to infinity. So that part, the constant part in the signal which keeps repeating, that time period of that constant part is known as the fundamental period of the signal. So this is all, like in layman terms. And even infinite time signals, there could be signals which are aperiodic, where the signal won't keep repeating. So take some signal like this. Maybe it is this, it is this, it is, it is this, and so on. So nowhere in the time axis the signal keeps repeating. So it always varies from minus infinity to infinity. There's like nowhere like the signal can be seen as some repeating signal. Such signals are known as infinite time aperiodic signals. But if there is some signal from minus infinity to infinity, if there is a part of the signal, if there is a part of the signal that keeps on repeating even towards the left and even towards the right, then such signals are known as periodic signals. And the fundamental period of the signal is the time period of the constant part which gets repeating across minus infinity to infinity. For example, in sine omega naught t, the constant part is in between 0. The constant part is in between 0 and 1 by f naught, and hence the period of the signal is 1 by f naught minus 0, which is 1 by f naught. Similarly, in this case, the constant part is in between minus 1 point. So this is the constant part, right? So same part keeps on repeating, even on the left, even on the right. So this is the constant part. So if you see on the left, you have the same thing that repeats, you have the same thing that repeats. And what is the time period of this constant part? 1.5 minus half, which is 2. Hence the fundamental period of the signal is 2. Is that okay? Clear? Can I go to the next topic?
Yes, ma'am.
Great.
Yes.
Okay, hope periodicity is clear. And yeah, there are other important things with respect to the periodicity. What happens to the period when you manipulate the signals? As in, suppose if you, right. Okay, so there are other two important properties. Time shifting will not change the period. Will not change period. Okay. So when you shift the periodic signal in time, so suppose if you shift this signal in time, so the same signal you move, right? When you move the same signal towards either right or towards left, the period, the constant part, uh, the time period of the constant part, that will not get affected when you shift, right? Hence, time shifting alone will not change the period, okay? But the other nice thing is time scaling does affect the period. Time scaling will affect the period. And how will it affect? Suppose if the original signal x of t period is t, then the period of x of a t is t by mod a. Remember? So why does this happen? Remember, when you have x of t, suppose if this is your x of t, the way you find x of a t is you divide the whole thing by mod a, right? I mean, you divide the whole thing by a in general. You divide the whole thing by a, right? So when you see the time difference in between this constant part, now even that difference get affected by a, right? So based on if a is positive, it is positive. If a is negative, so the sign gets varied. So if you look at it, if x of t has a period of t, then x of at would have a period of t by mod a, right? Because the period is always positive, this difference, So if this difference is t, when you time scale the signal, that period would be t by mod j. You see that, right? either the signal gets compressed or the signal gets expanded. So this, and the constant part also, either it will get compressed or it will get expanded, and hence the fundamental period also either it gets compressed or it gets expanded. Okay. So these are like two important properties which I hope you would remember. Sorry, which I hope you would remember. So yeah. So next part is manipulation. I'm sorry, I'm in a hurry because I have to leave today soon. But yeah, grasp as much as you can. If you have more doubts, we can also discuss on next Wednesday's discussion. So yeah. So this is time shifting will not change the period. Time scaling will affect the period, and the effect is like this. Okay, is this okay? Go to the next part.
Yes, ma'am.
Right. And the next part is manipulation of the signal. Suppose you take two signals, x1 of t and x2 of t. Let the period of the signal is t1 and the period of the signal is t2. So what happens to the period of the signal x1 of t plus x2 of t? The first question is, will this be periodic? Suppose these two are periodic signals. Okay. When you add the two signals, will periodicity retain? So how do you check if the periodicity retain or not? So first find the t1, the period of the first signal, and the period of the second signal, and try to evaluate the fraction t1 by t2. So evaluate t1 by t2. If this is a rational number, then x1 of t plus x2 of t, or any manipulation like x1 of t multiplied with x2 of t. If the fundamental period of the first signal divided by the fundamental period of the second signal is a rational number, then even these signals are periodic. Okay. And what is the period of such a signal? So t1 by t2, if this is some rational number m by n, where m by n is a rational number, then the fundamental period of the manipulated signal t is either nt1 or mt2. Okay, so this is the formula to it. Or you can also evaluate this by calculating the LCM of the two numbers t1, t2. Or this is also an easy to do. Okay, is that okay? So I will repeat this again. So take any two signals. Let x1 of t be periodic signal with fundamental period t1, and x2 of t be periodic signal with fundamental period t2. Two manipulations that are possible are x1 of t plus x2 of t and x1 of t multiplied with x2 of t. I'm not writing x1 of t minus x2 of t and x1 of t divided by x2 of t because these two can be represented using these two manipulations. This is same as x1 of t plus minus x2 of t, and this is same as x1 of t multiplied by 1 by x2 of t, right? So these two operations can also be defined using these two operations. So I'm not writing these two operations. So now the question is, are these two manipulations, will that aid you periodic signal? So how do you check if that is a periodic signal? Evaluate T1 by T2. Okay. If T1 by T2 is equal to sum by m by n, if it can be written as sum m by n form, which is a rational number, then the manipulation x1 of t plus x2 of t or x1 of t multiplied with x2 of t are periodic. If this is not a rational number, then they are aperiodic. Okay. And how do you find the fundamental period for this manipulated signal? Fundamental period t of x1 of t plus x2 of t, or x1 of t multiplied with x2 of t, is simply LCM of t1 comma t2, or you can also easily find this as, so remember you have this, right? So from this, t1 by t2 equal to m by n, which implies n times t1 is equal to m times t2, right? Which implies your fundamental period of the manipulated signal is either nt1 or mt2. Okay, is that all right? I need some acknowledgement, quick.
Yes, ma'am.
Okay, so this is something you may like and you may remember. This is a nice thing to do. So some quick example. Suppose you have sine t plus cos pi t. Is this a periodic signal? So this is my x1 of t. This is my x2 of t. x1 of t is sine t. Remember the periodic. So this is sine 2 pi star 1 by 2 pi star t. This is your f naught. And the fundamental period t1 is 1 by 1 by 2 pi, which is 2 pi. Correct? Correct? Need some acknowledgement? Able to follow?
Yes, ma'am.
And x2 of t is cos pi t, right? So this I can write as cos 2 pi star 1 by 2 star t. So this is f naught here. Implies t2 is equal to 1 by f naught, which is 1 by 2, simply 2. So when I calculate t1 by t2, this is simply 2 pi by 2, which is pi. Pi is not a rational number. Okay. Hence,
Ma'am.
sin t plus cos pi t is not periodic. Even though the original signals are periodic, sin t is periodic, cos pi t is periodic, but since this did not give you, since this fraction did not give you a rational number, the sum is not periodic. Okay, is that all right? Likewise, suppose if you have sin t plus cos t, then t1 by t2 would be 2 pi by 2 pi, which is 1, right? Or let me take this cos 2t. Okay, so my t1 is 2 pi from the previous example. T1 is 2 pi. Cos 2t is cos 2 star pi star 1 by pi star t. F naught is 1 by pi here. So T2 is 1 by pi, which is pi. So T2 is pi. Hence my T1 by T2, if you see, that is 2, which is a rational number. Hence this is periodic. And what is the fundamental period? T is equal to either T1 or 2T2. Okay, and what is T1? That is 2 pi, or 2T2 is also 2 pi. So the fundamental period of this sum is 2 pi. That is how you have to evaluate. Okay, I hope this is clear. Can I go to the next part quickly? Yeah.
Yes, ma'am.
Right. So I'll quickly tell you about the energy and the power, and I'll wrap today's session because I have a really important, I have to go for another work today. Okay, so energy of the signal energy of some signal x of t, which I denote by Ex, is defined as minus infinity to infinity x of t whole square dt. Okay, so this is energy. To calculate energy, you have to know some simple integration technique. That is all it is there to calculate energy and power, nothing else. And similarly, the power of the signal is defined as limit t tending to infinity 1 by t minus t by 2 to t by 2 mod x of t whole square x of tau whole square d tau. Is that correct? Yeah. Okay. So this is power. Some important things. Suppose x1 of t and x2 of t are orthogonal, then energy of x of t, which is the sum of the two signals, Ex, is Ex1 plus Ex2. Okay. This is one important thing. And for all finite energy signals, all finite energy signals have power 0. So suppose Ex is less than infinity, implies Px is 0. You don't even need to evaluate the power for such signals. Okay. And likewise, if Px is greater than 0, if there is some power in the signal, then Ex is 0. Okay. So if you evaluate the energy and if it is less than infinity, then you don't even need to evaluate the power is 0. If you evaluate the power and if the power is finite, then you don't even need to evaluate. So if the power is not finite, if the power is greater than 0, even if the power is infinity, so you don't even need to, there won't be actually any infinity power, but yeah, you don't even need to calculate the energy, and the energy of the signal is 0. Okay. And signals with finite power, if Px is less than 0, then such signals are called power signals. If Ex is less than infinity, then such signals are called energy signals. Okay. Take this note. So I think your week 3 assignments focus only on this part. There's another part to it. Suppose x of t has energy Ex, then x of at plus b has energy Ex by mod A. But if x of t has power Px, x of at plus b, the power remains the same. There's no change in the power. Okay. These are two things that you may have to remember in order for you to solve your week 3 assignment. So week 4 also has some discussion on power and energy of the signals. I'll take it up from here in our Wednesday's class. Is that okay?
Yes, ma'am.
We'll also upload this recording on YouTube if you have missed any parts of this. But yeah.
Can you please send the link of YouTube channel? I cannot get it.
By today? Yeah, definitely. I'll do that. Yeah. I mean, Google takes some time to process, so by tomorrow, definitely we'll upload. Is that okay?
Thank you.
Yeah. Thanks, guys. Thank you, guys, for joining. Yeah. Bye. I'll meet you on Wednesday. I'll see you Wednesday. Yeah.
Thank you, ma'am.
Yeah. Bye.